Hello everyone, how are you guys doing? I hope you're all doing amazing. So I'm seeing on this side. Today we will be working on some YOLO models. So what exactly are we working on? So you must all be aware of Ultralytics if you have worked on YOLO before. So YOLO is basically a very standard kind of a model that is used in your object detection, object segmentation, oriented bounding box, and those kind of data sets. Now for classification problems as well. So for computer vision, most of the deep learning problems that you get. So just to list it all down again, object detection, object segmentation, object classification, your oriented bounding box detection, stuff like that. So these kind of models are available from YOLO. So YOLO is just a standard set of architecture that is used. So there are multiple versions to YOLO, and Ultralytics is a company that has provided a very clean interface, a very clean Python framework to work with YOLO. So today we will be working on the Ultralytics models. We'll first train a model from scratch on a oriented bounding box task, and then we'll try to convert that model from Ultralytics flow, which basically uses Pytorch in its backend, which is comparatively slow when it comes to compute efficiency and memory footprint and stuff, and you have to load a very large framework as such to just to run inference on your models. So instead of doing that, we want to do this with the help of a ONNX pipeline. So ONNX-Runtime is another framework that is commonly used, which helps us run these computes faster, and at the same time ONNX-Runtime has a lower footprint because it is just used for inference. So let's get this session started. So first of all, we'll be working completely from scratch. I'll be setting up the environment for Ultralytics, and then we'll start working on the models and stuff like that. So hope you're in it. So let's get started. So this is what Ultralytics look like. I hope my screen is visible. Yes, it is. Cool. So this is the Ultralytics documentation. This is the dataset we'll be using. So there are multiple images in it. Some are based on ships, some are flights, some are your lawns and stuff, that kind of things. Okay. And let me quickly show you how to install Ultralytics. So I'll just say Ultralytics GitHub. There you go. Ultralytics. Nice. So recently YOLO V11 was also released. I hope you must have heard about it. It was a really, like, at this point there is not much improvement they are doing because YOLO has already pushed the boundaries too far. But with each model they are able to reduce the compute speed and also improve the overall accuracy, which is generally measured in terms of mean average precision when it comes to your object detection and segmentation tasks. So now I'll quickly open up my VS Code and we'll start setting up our environment. Let me just open up a new file, new project, Python, YOLO, ONNX. So in this first video in this series, it's gonna be a series, by the way, if I have not said that before. So in this series, the first video, we are gonna be working with oriented bounding box kind of models. So oriented bounding box is, if you have heard of a detection task. So in detection task, you are basically trying to detect a box around, detect a rectangle around a particular object. So let me just show you the image. Um, So this is what it generally looks like. So you have an object, you create a rectangle around it. Now this rectangle has to be in the same orientation as the image. So basically the rectangle cannot be rotated. Now when it comes to images like these, where you have to detect the rectangle, but you need slight more improvement. You don't want to segment the image, as segmentation can be too complex when you're talking about such data sets, but you at least want to be able to uh, rectangle, make a narrower fit on the rectangle on the image. So that's why when there comes in your oriented bounding box. So here you can see, compared to the images that I just showed you, which is normal detection models, where you just create a bounding box which has to be perpendicular or in the same orientation as the image, as I like to call it. But when it comes to oriented bounding box, it can have a rotation element as well. So that's what you get as extra, and you can have narrower fits in your images. So that made sense. Now we'll quickly go and install and set up our environment. So I'll be using UV for setting up my environment. Yeah, so UV is a new tool which is written in Rust and helps you set up your environment. So it is pretty much like poetry and stuff, and it uses PyProject.toml, which is I think it is cleaner when compared to your classic requirements.txt, as you have to mention your version specifically and you have to take care of which of the libraries you have used. But when you're using Poetry or you're using ONNX-Runtime, you can directly add the library you want and the versions and stuff will be saved for you as well. So versioning becomes easier. So we'll just say UV init. This will initialize our environment. After that, we'll say UV-venv. This will create our virtual environment. And now we can say source.venv bin activate, and you have your virtual environment activated. Now we don't need this hello.py. What we want to do is I'll just have them side by side for now, as I might be requiring a lot of documentation reading and stuff, even when we'll be going towards ONNX. This is me trying to do it. I have not done it before. I tried to do some of it, so I have some code, but it's not completed yet. So we want to create that library. And if it works out well, after completing all three different types of model that there exist in YOLO, so detection, oriented bounding box, segmentation, classification we can also do. Classification must be much simpler. So when we are done with all these four types of models, we'll try to run them through all the YOLO versions and see if our ONNX pipeline is working. And when it is, we can easily set up a framework or upload this library at open source so that you guys can work with it. And it will be really cool because everyone will have faster compute inference speeds. So great. And lower memory for that. So that will cost you that will save you some cost when you are trying to deploy that. So yeah, that's cool. So let me just set it up. I'll first have to install it. So I hope the name is Ultralytics only. So yeah, so you just say UV add Ultralytics. This will install the library for you, and at the same time it will also add it to your pyproject.toml, which will help you later in the process. So cool. So this is much more of a benchmarking. Now I want to create a separate environment for my ONNX because I want to also see what kind of a space they both are taking. So that would be, so this I can rename the folder later, but basically this folder is where we're going to be benchmarking our current Ultralytics implementation, train a model, and then get the inference out of it so that once we have something to compare with our actual ONNX runtime based inference. Cool. So let's go to hello.py. Let's rename it to training. Training we'll still do in Ultralytics. We don't want to do training in ONNX. I don't think it even supports training. It is majorly for inference itself. So yeah. So I'll just go ahead and remove all of this. And we'll say from Ultralytics import YOLO. That's majorly what you're gonna need. It's a very cleanly packed framework for that. So yeah, I'll just copy this YAML file. So I'm gonna be using this dataset. So Dota is a famous dataset for oriented bounding box, and Dota 8 is a smaller dataset in this Dota thing, which would be enough for us as we are trying to train a model fast. We can also do this inference on Google Colab because I think it will take a while, but okay. Or maybe Kaggle. Kaggle can work for that case. Yeah, we'll just set up the code here and we'll see if it is working or not. And once it is working, we'll set up the training on that interface. Cool. And we'll have a untrained model here just to so that at the same time we can start preparing our ONNX runtime code. We don't want to waste any time, do we? Cool. And I know I need to stop doing these kind of spontaneous streams as you guys are not aware of it and you are guys not able to join live and we are not able to have the discussions that we want to have during the meetings. So yeah, there's that. Now let's start with the training part. So we just need this Dota YAML file. So just create it Dota v8.yaml, and there you go. That's all you're gonna need. This will automatically download these images for you in this particular path. I don't think we'll need to do dot slash. Let's just do dot slash dataset slash data add, and then from there you'll have your images, you'll have your train, your validation, and this all will be downloaded from this link. And you're just gonna go in your training.py and we're just gonna run this. So model is gonna be YOLO v11 Okay, they removed the V from this for some apparent reason. And there you go. One more small tip for anyone who is using a MacBook and want to train a YOLO model: never use MPS devices for training your models, as they have, I think, they have a lower floating point precision or something, and that's why their models you will get from ML, your metal device, when you're training on it, it will not be good. It will not be enough for you when you're trying to train a good model. So yeah, just keep head on that. Use Google Colab, it's free, and YOLO models doesn't necessarily take too much time on training if you don't have a very big data set, as you are mostly trying to just fine tune the model. So everything should work out fine for you on a Google Colab enough. So epochs, I don't know, do you need to set epochs? Yeah, let's keep them 100. Image size 640, keep everything standard. Cool, so this is what we have. This is what we want to run, so we'll just quickly check it. I'll be using this kind of a REPL thing. It's easier for me. It helps you create your Python script, but at the same time, okay, pip installer. So when you're working with a UV environment, you don't generally get a pip installer inside of it until and unless you add the tool for it. So you just want to run UV add ipykernel. Cool, and now this should be working. Yeah, let's go. So we would just want to see if the training has started or not, and if it is working properly, then we can set it up on Google Colab and start the training, and at the same time we'll start working with the untrained model. And to save the model, I think they have something of their own. I'll just have to quickly check. I think it saves automatically. Well, at the time of training, I'm not getting any prints for now. Okay, now we're getting it. Creating a new Ultralytics settings file, blah 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 blah, downloading the this is downloading the model. Now you are downloading the dataset. Cool. That was a small dataset. I thought it would be bigger. Okay. Let's go. Okay, we have received an error. Error loading data. Datasets, blah 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 blah. C for dataset formatting guidance. What happened here? Let's see. Did we download something? Datasets, Dota 8. Maybe some kind of a file naming error. Okay. Path to images. Now the images must be in dataset slash dota 8, and then you have your images, your labels. Inside images you have your train inside. Okay, why do I have just 4 images? That will not work. Is dota 8 not the right dataset? It's too small. Okay, let's use another dataset then. Dota 8 is too small, so let's see what else do we have. Dota v2, you can go ahead with this. No, but I want to use Dota v2, right? Why have they named it Dota v2 if they have Dota v1 everywhere else? Okay, we can use Dota v1 as well. It shouldn't matter to us. So let's go ahead and download this data. If nothing works out for us, we'll just download a segmentation dataset. There are plenty of segmentation datasets available, and we'll just run OBB on it by basically fitting rotated rectangles to that segmentation results first of all, and then just so for that we'll be using OpenCV, and that's how you can do it. So I'll just close this window if I can, please. I'm just not able to see. Okay, cool. So what we want to do is we want to first convert this YOLO 8.yml and delete this. We don't need this datasets. Again. Cool, and here we want to replace the script with our Dota v1. Cool, so this should be here. You have your train well test, and other than that, you want to do first of all is split your dataset. Okay, so we are just using the documentation right now. I have not downloaded this dataset from YOLO before or something like that. Never got a chance to do it, never had a need, but it should be super simple. So this is what we want to do. But before that, I think we'll need to download the data. So to download it, okay, one simple way is we can just, rather than having a download script here, we can just quickly download it manually just to avoid any issues. Yeah, there you go. It's gonna go in your documents, projects, Python, and your YOLO ONNX. Yes, there you have it. You just want to save it here. 1.9 GB, that's what I expect. What was that? That was too small. 1.5 MB, you're not getting any data from that. And at the same time, I think we'll have to upload it on Google Colab if we really want to train on it, or we can use it from Kaggle itself. We'll have to see about that. Okay. Once we are ready to train this, our next step would be to start working on the ONNX-Runtime thing. So until then, let me just quickly show you what ONNX-Runtime looks like. So this is your ONNX-Runtime library. It supports multiple languages. So you have Python, you have C, you can also run C#, JS, JavaScript, C++, all of these languages. So it allows you to run your inference on multiple different languages and have a standard model format for it. So your format would be ONNX, and the runtime would be faster because you are not loading in too many details that you have to do in Pytorch and stuff, because you're loading too much unnecessary things when you're working with Pytorch, because you don't need that training, you don't need that autograde functionality and all of those kernels and stuff. But here you're just getting what you want and you can run inference on it. Okay, so there is also training on it. I've not sure I have looked into this. Maybe this will be something interesting too that we can tackle in another video. But for now, we just want this data set to be downloaded quickly, and then we want to work on our training part. So let's see. Till then, if we can at least get it to train on that data set, data 8 or whatever. I don't know what error was there. I use the same things as they are. There must be something small issue. So you have this, copy this, you go to your training.py, you download this for now, and you download this like that. Let's see what we are facing now. YOLO model should have been already downloaded. Yeah, there you go. And you downloaded your data set. Let's see, we'll see the same issue or not. Okay, seems promising till now. Okay, images have been cached. Cool. So it is working. I guess that dot slash, okay, that's a bit weird. Why you have to, I thought the path should be defined from here, but I think it needs a required path from somewhere else, because where is it going inside to? Yeah, the dataset location doesn't make any sense, but okay, it is working. So you have your first epoch here. Okay, this dataset is very small, so the epochs are running up pretty quickly. So we can have, are we saving it in some instances? I'm not sure if I've given the logic to save it on different checkpoints. Let's see if we are still. Best and blast. Okay, that's fine. So this should be enough for us to start training our, until and unless we are downloading this dataset. Till then, we can start working with this models and try to train our own NX thing on this. So let's see how we can convert this PD files. So first of all, I want to quickly show you how you can convert your PD files, which is your Pytorch model weight files, to ONNX files. So for that, we'll be using, was it DeepMind? It was not DeepMind. It was DeepSparse. Yeah, DeepSparse YOLO to ONNX. Yeah. So they had shown this code how you can convert your models from YOLO to ONNX. So let's see. I'll just quickly copy this up. Excuse me. Cool. So what you want to do is, I'll stop this training. I don't want to train on these four images. Testing would be on those large amount of data set, but this is enough to get a points and start working on our ONNX and comparing the results if they are exactly matching or not. That's what we want to do. So I'll just interrupt the training for now. I'll close this session up, and yeah, this is all that we need from this. Now we'll close this. This is your bigger dataset getting downloaded. Till then, let's start working on our ONNX pipeline. So I want to do that memory footprint testing kind of thing. But so let's not do it for now. I want to create a separate environment for that. Now what I want to do is I'll use this command line interface to, I'm going to do this. No, none of that. This is not the code I was looking for. Yes, this is what I'm looking for. So what you want to do is YOLO task is equal to OBB, mode is equal to export, model is equal to YOLO. So you'll have to give the path of the model here, which would be in our case runs. Well, I'm not getting it. Ah, shit, it's not auto completed. Okay, we'll have to write it manually. OBB train 2 weights best.pd. There you go. This should be enough. Let's just quickly wait for it to get done. We'll also store this command in our readme because we'll be needing it throughout our project. And okay, we just faced another bug. This is no module named ONNX. So we'll just quickly go and install ONNX-Runtime. I think that's all you need. Or we'll just, I'm not sure. Do you need ONNX or ONNX-Runtime? That's a bit confusing. Let's just quickly check out the documentation. Let's see what you're facing right now. Just tell me what I need to install. You want ONNX. So we'll just go and add UV add ONNX. Again, we are using UV, so we are keeping track of all of the libraries we are using right now in our pyproject.toml file. So you can see all the libraries are installed till now. They are stored here for me, and it will make my life pretty easy when I'm trying to move this from one system to another. And now we'll try our command again. Cool. I think it ran successfully. Let's just quickly go and check it out. Train 2 weights, and there you go. You have your best.onnx weights here. So cool. So for now, I'm writing this ONNX runtime code right here in this library. But okay, no, wait. I don't want to do that. If I'm writing this down here, then we'll again face some issues. So okay, so let me just copy everything down to another project. I'll be creating two projects. One will be where I'm storing my Ultralytics runtime, and one project will be where I'm storing my ONNX runtime because I don't want to mix and match them. Well, I want to check how much memory each of them are taking. This memory thing starts to matter when you're running multiple instances of your code, because at that time you want to have enough resources or enough memory, and it will be loaded on every single processor differently, and that will cause your memory to jump up. So you want to reduce your libraries and stuff as much as possible, so that when you're dockerizing it or you're pushing it to some kind of a online interface service, some AWS, some Google Cloud, anything like that, you will be saving on some cost by running it on ONNX, by saving some storage, so that you can have more processors running at the same time. So okay, I hope that made sense. Now I'll just go and create a new project. That's what I was doing. Completely got mixed up. So YOLO ONNX and then experiment. I'll open this up, and what I want to do is I want to copy some of the files from here to here. So we'll just copy up the whole runs thing, because why not? And also the whole dataset thing. I want to go there again and again, and that should be enough. So I'll again create a UV environment. You know how it works till now. So UV init, UV vent, source. Nope, that's not what I wanted. Dot vent. I think my screen must be too small right now. Let me just quickly change that. I think that's all we needed from this thing. We'll get our dataset downloaded, and then we'll start working on a real model, so that we can also have some model trained at the same time. Yeah, this was just me making the thumbnail for this video. I hope you liked it. But whatever. That's not one of my concerns. This is not the kind of a stream where you watch thumbnails. You watch code here. So yeah. So now that we have, so let's rename this hello.py again to something else. ONNX-Runtime py. Now the tricky thing is, when you're running your inference on YOLO, you get some benefits because they have written the post processor and pre-processor for you. But when you start working on some compute engines like your deep sparse, which I'm not working for right now, that may be the next step that we work on. But I want to work with something that is more commercially viable and is being used in the market. Deep sparse is more of a new thing that is not being tested yet, and they are also using some kind of a floating point reduction, accuracy reduction. So I don't want to do that right now. I want to match them as exactly as possible. But okay, and yeah, data download we did already. Now what I want to do is, when you're running an inference on your classic YOLO and you're using Ultralytics to run inference, let me just quickly show you how it looks like and how seamless it is. So you go on your training.py, your model is trained, you're like good, then you don't need to run all of this. You just, okay, so let me just separate my imports. You run this, you're like, hey, what my model is YOLO. You give his path, so your runs, train2, weights, and your best.pd, and you're like, okay, my model is here, I want to do predictions. So what do you want to get from predictions? You want to get your oriented bounding boxes. And how do you get them? You say your result is equal to model.predict, and you give the path to your image. So the path to your image, you go to your data sets, go to your images, go to val, and you pick any random one of these. So let me just copy the relative part directly. So let's do this. Cool. So you do this and you print your result. And what happened? Oh, runs OBB. And you get your results. Now you see something amazing in here, don't you? Just look at the results. You have your OBB, your boxes, key points, mask, names. It's so well organized. You get everything that you want from it. You don't need to write any code. It's just super clean. Now let me just show you that. Results.obb, result 0. You can use run batch, so therefore it gives you a list, because you can give a list of images in here. And you say .obb, and you just print that. and you look at that. You can get it in xy, where n is supposed to be your rotation, I think. xy, so you get the 4 points for your rotated bounding boxes, because 4 points are enough to give you any rotated bounding box. You get your xy, where you give your top point and your top left point and bottom right point, and you have your xywhr, where you give your center xy, your width and height of the image, and the overall rotation of that rectangle. You get all of these formats instantly, and you can get your data. You can plot it super easy. Let me just even show you the plotting thing, because it's so simple. I can just write it without worrying about anything. So I'll just import this. Oh, so tiring, so easy. I don't even have to use my brain. Result.obb.xyxy. I'll also import Shapely. I think I'm not. So I'll just go ahead and say source.when bin activate. You go UV at Shapely. Done. You run this, and you finally say you want your xy, and you want to make a polygon out of them. And what you want to do is you want to say your x comma y's are going to be polygon dot exterior dot xy dot xy, and you say plot dot I'm show, and okay, you'll have to import cv2 as well. I'm just import cv2. cv2 is here just to read the image. So what I can do is, instead of passing the image like this, because I'm reading it anyway, I'll just do image is equal to cv2 dot I'm read, and I'll pass in the path of the image there. You know, you see another beautiful thing. I was just giving in my image path till now, but now I decided no, I just want to give you an image directly, and it will figure it out for me, because the framework is so clean. I don't know how many times I'm gonna say it this time. But there you go, you get the same fucking results. Nothing changed, right? Let me just quickly verify. So 78, 79, 70, 79, 80, 71. I hope you remember the numbers. Now I'll just remove this and pass in the image directly. So numbers again, 78, 79, 70. 3 will be enough. Oh, we can just directly compare. 78, 79, 70, 79, 80, 71. 79, 80, 71. So you get the fucking same results. Ah, fuck, my leg is sleeping. Wake up. Ouch. Sorry, guys. But okay, so you get your results. You can get pass in the image directly, and the framework will figure it out for you. Now, what I want to do is, you get your image. It's restarted. Okay, so you do this. You don't want to run that because you have already trained your model. I'll just comment it out and write down that I've trained the model. By the way, who if you are not aware of this thing and you are thinking what kind of magical syntax I'm using, this is REPL runtime, which is available in VS Code by itself. And what you can do is you can just add these kind of comments on top of your VS Code, and it will convert them into similar blocks as you have in your Jupyter notebook. Now, what I personally feel is the benefit with these are that I can easily write my Python code as I'm writing, and I can test it block by block, and I don't have to copy and paste them to make a Python class or something afterwards. I just can directly use this because these are just comments that will not matter to my pipeline. This is just something that VS Code is interpreting for me for now. So these are kind of cool. Now I just run this, I got my results, I'm so happy. I print my polygon, I'm gonna plot my image. I'm gonna go plot x comma y and plot.show. I'm also gonna plot oh, shooting off my axes as those are not necessary right now. Sorry, what happened? Invalid reduce pass to linear in constructor. Are you kidding me? Let's just quickly print it out. That is not possible. We are doing a blunder. What the hell am I doing? Thank you. Boom. Did it get printed? Yeah. So you have a, okay. So basically you have one more dimension in here. You just want two dimensions. So I'm just gonna say 0 here. This should work. Oh no, that was stupid of me. So this will plot one of the OBBs, right? So to this, what I have to do is for I in range, whatever. Do I need a range? Yeah. So, or you can just go for your oriented bounding box in result 0 dot obb dot xy. You want to do this. Yeah, that's how you do it. Stupid idiot. And you want to plot this outside of here. And what this should allow you to do is you plot all of your oriented bounding boxes. Not yet. What went wrong? Oh yeah, we are not passing it here correctly. So you want to do is oriented bounding box. And there you go. You get all of your 4 boxes. Well, for 24. I mean, it must have overfitted it for now. But for 24 training on such a shitty data set of just 4 images, the model is doing pretty well in itself. Yeah, the images are pretty different from the testing images. So good, we have something. We have a model that is somewhat working, and you see the boxes are not particularly straight, they are rotated. So this is how you work, and this is super clean. You get it in whatever format you want, everything is written for you. There are loads and loads of coding going on in the background. You go to this, you see all of the things that are happening in the background. It's just super convenient for you. But when you want to boost the performance, you'll have to get out of your comfort zone. That's how the world works. Now, what I want to do is, going back to our ONNX-Runtime, you will not get the advantage you were getting of these pre-processors and post-processors that are able to give you this in any format and read any format for you. So how do you deal with that? So first of all, let's go here and let's set up this environment. To set it up, basically we want CV2 in here. We want our let's just start adding. So you want CV2, open CV Python. You will also want, most probably, we will be working with NumPy. So let's just add it. Okay, OpenCV already added it. I didn't see that. You cancel this. Other than that, you will need your ONNX-Runtime. That's the most important one. What happened? Is ONNX-Runtime not supported for Python greater than 3.12? Are we on Python 3.13? Okay, no problem. Yeah, so what we want to do is we want to delete this, delete our virtual environment, delete the Python version thing, project.toml, everything has to go away, don't worry, it will all come back. And one simple thing, when you're doing UV init, you want to describe your Python version. Let me just quickly check how you do that. Okay, I think UV init you can do directly. No, but it takes a Python version on itself, right? So you want to do UV init with a Python version as well. Okay, cool. Let's delete all of these again. Three point 11 should work for us. Now Python version must be fixed. Cool. So now you can do UV and it should conform to the Python version that you were just using. Yeah, it just downloaded 3.11 for me. And cool. So now the ONNX-Runtime thing should work. So I'll just go UV add and I'll again add my CV2. So open CV Python. I also want to add my, what else do I want to add? I want to add my ONNX-Runtime. This is what this video is all about. What the hell is happening? No solution found when resolving dependencies. Platform system is equal to because ONNX packages in your project depends on ONNX-Runtime. Okay. Let's see what the hell are we facing now. I know it works. Jenny, oh, this is spelling incorrect. You don't want to put this hash in there, right? Okay, so 3.12 might have also worked, but now you know how to do Python version changes when you're using UV. Cool. So now that you have all of this working for you, I'll just again delete this hello.py. No one cares for it. Now here, first of all, one thing I want to do is read my image and see what is visible to me. So import matplotlib.py.splt, and I want to import cv2. For now it doesn't know which Python version I'm at, and also I'll want to add ipy kernel because I want to work with a REPL kernel and I don't really want to use Python, and like in that sense where you use Python CLI to run your programs. That will be a job for later. So let's just run this and it should be able to figure out the versions and everything itself. No module name matplotlib. Okay, uv add matplotlib. I think I had already added OpenCV Python, so CV2 should be there. Let it run once and it should be able to figure it out. It is working. It is taking some time. Let's see. Now what we want to do is we want to get a, okay, so the imports are working now. It's still showing them as this for some reason. I'm not sure why. It would be better if it can show it correctly. Do we want to turn back to 3.12? Let's turn back to 3.12. This will get annoying. Sometimes the older Python versions, this thing, did I just fucking delete it? I want to delete that. Delete every other thing in here that I don't want. And now finally, peacefully, I'll say uv init Python. I'll not even specify Python. It should get the latest one for me. And is it the latest one? Yes. 3.12 is not the latest one. There is 3.13. But okay. uv-venv, create your venv, source.venv bin activate clear, delete this. And what you want to finally do is uv add matplotlib, uv add OpenCV Python, uv add ONNX-Runtime, this time not doing the spelling mistake. And what else? Do you need anything else? I don't think you need anything else. Do you? No. Cool. Maybe we'll need anything else, but okay, we'll just keep adding it on the fly. And so yeah, see, it just popped up. You needed something else. You should have focused on it, Ducky. What the fuck were you doing? Why can't you even tell me these simple things? Okay, you have this now. Great, all the efforts wasted. It is still not showing me, so it will not give me these hints that will help me code faster, but whatever, that's what I have to live with. Now what I want to do is I want to quickly show you what my image looks like, and then we can start working with a sample image. So I'll load up an image from my data sets. I'll just copy the path because the name is going to be super weird. Copy, not copy, just copy this relative path, and there you go. Bam bam smam. Your image is here now. Once you have loaded up your image, you can just say, let's keep the image loading separate. plotting image, and in the plot of the image we want to show image is equal to cv2. What the fuck? Plot dot im show image and plot dot show. Now when you do that, you'll be left with this. So you have your beautiful image here with you. Now what to do with this image? So let me quickly show you what ONNX-Runtime's output looks like if I don't do anything with that. So let's see. So ONNX-Runtime. When you're working with ONNX-Runtime, you have to start a session and then you just keep giving it your batches. Now you'll have to quickly look at the documentation to see how it works. So there you go. You give your model path and you start a session. And so yeah, so let me do another cell where we'll say loading our model starting session, and here you will load up your model. What the fuck just happened? Excuse me. Nope, I didn't click you. Magic happening in the air. And what do you want to import? Okay, you like your own cool name, huh? ORT. Okay, fair. I'll give you that. And your mother path will be again your runs obb train2 weights best.onnx. This should load your model and start your session. Now once you have your session started, what you want to do is just input your image into it. Now before inputting the image, okay, let me just show you guys how it is working. We will discuss as we'll face the errors. So yeah, I started the session. I was very habitual to my Ultralytics smooth flow where everything was taken care for me. I just sent in the image, the model was working, everything seemed so pretty, so easy. But here you go. Now you have your image. I want to keep the plotting separate. I just want to get the results here. So what I do is I'll do session, and how do you actually do that? Dot run. So output is equal to session dot run. This is your output name. You don't need to specify it. We are specifying outputs here, so we don't need to do it. We specify our input and we give in our image. Everything was working like this, right? This is exactly what we did in Ultralytics. It's exactly what we did when we were using Ultralytics. This should work, right? I'll just print my outputs. They should have that XY, XY, XYR, all of these beautiful things. It's working. It's running something. Are we stuck somewhere? We're stuck on loading our model, is it? Let's restart everything, clear all, so that we can see what's going on more clearly. So you run this, you load your image, you have loaded your session, how it is working, and you get an error. Okay, this is a more tolerable error, but okay, what you get? So okay, this is simpler. So images are missing in the input feed. So what you want to do is instead of this, you want to give your images, right? ONNX-Runtime invalid argument, expected data type, actual tensor uint8, get tensor float. Huh, what happened? You're getting an error. But this is simple. I know how to solve this. Son, this is very easy. Do not know about data types. We just have to convert this uint8 into float. So how do you do that? You just np.dtype, they are not imported numpy yet, so import numpy as np, run that and do np.array, and you say dtype is equal to np.float32. This should work. No, still doesn't work. expected 4 got 3. Now what is that? That is coming because it expects a batch of images, but you're giving a single image. So you will have to add a new access to the image. So how you do that? You again go np, so you keep a np.new access and everything else remains the same. So now this error should be fixed. But now I got another error. What the hell is happening? Ultralytics was so simple. This model was just running. Okay, so now you get the error that your image size is not matching. The model expected the image size to be 640 by 640, but because Ultralytics was taking care of all this pre-processing for you, you didn't even realize that you're giving an image in a different dimension. Not dimension, in a different size. So what do you want to do? You want to resize the image. So you go here and you say image is equal to image.resize. Not this, reshape is different. Resize it to 640, 640. Okay. Bam, bam, bam. Another error. What's this? This one even I don't realize what is this. Image.shape. I don't think you need to call it. Runtime object has no attribute shape. Image is a runtime object now? What the hell happened to image? What the hell happened to my image? How do you resize? Am I doing something wrong with this? But it should give me an error, right? CV2 to resize source, blah blah blah. There's a simpler way, right? Okay, let's do it with CV2 to resize. Because why not? I mean, I might be wrong about the resize thing. So image, comma, dimension. So I want, what is dimension? You want the size, right? Dim is width, comma, height, exactly. So 640, comma, 640. Hunky dory. This is working now. This should work now. This should work now. No, it didn't. Because Pytorch generally wants you to keep your channels at the very end, but ONNX expects you to keep your channels at the second position. So now you also want to permute. How do you do that? Image is equal to we can transpose, right? Between the axes, so we want our two axes to be replaced. So we want the second axis to be replaced. No. It's not easy as transposing. What we want is something different. So numpy alternative to torch permute. I must have something like that as well. So what did I do at the time being? I just said new shape, whatever. CV2.resize, I did that. Copy make border, transpose. Yeah, okay, so I did two transpose. Very weirdly though. Let me check. Is there a better way? Pytorch permute equivalent numpy. Wow. Moved in, move access versus permute in Pytorch. But they're not talking about numpy, is it? No, don't want it if it is not numpy. So yeah, let's look at this. What is torch? Blah blah blah. We all know what torch is. Okay, so let's do one thing. So we have your image which has your BGR to BHWC2. Okay, so one more thing is that your image is BGR. You want it to be RGB, so you want to reverse the image as well. before passing it inside of your model. Now again, YOLO was doing it for you, but you can't do it here. So CV2 by default read images in your BGR format. So this is BGR, this is still BGR. You want to convert it to RGB. So what you do is, okay, so why do we even want to do this here as well then? Let's bring all of this above as well. So we'll have our pre-processed image as something else. So let's say I want to define a code for our preprocessor. Image preprocessor, and you send your image path in here. Let's keep it super clean. Now what you do, you open your image from the image path. I'll just copy this somewhere. There you go. And in the preprocessed image, you want to read image path. This is BGR right now. This is again BGR. What you do, you say image is equal to image. So you reverse the image, so now it is RGB. After that, you also and also I'll write the shapes here. So this is some 1024 comma 3. Now you have made it 640 comma 3, and then again it is still 640 comma 3. Now one thing you wanted to do was image is equal to image, and you wanted to do np.new access comma dot dot dot. This makes your image. Now okay, let's also put this in here as well. So your image is HWC, height width channel. Now it is height width channel. Here also it is height width channel. This is how the image is by default in CV2. Now to convert this to this, now it is BHWC. So batches you have added basically. So batch height width channel. Now what you want to convert this to is so convert batch height width channel to batch channel height width. Correct? Correct. So to do this, what do you do to achieve this? Now one simple thing is you do image.transpose and let's just quickly see how transpose works if we give it multiple inputs, because I'm not sure I remember why I did the transpose like that. Let's say numpy transpose for 1D array. This returns an unchanged view of the original array as transpose is vector with this. Okay, so you give your input and you give your access. If specified, it must be a tuple or a list which contains a permutation of 0 to n, where n is the number of axes of A. Negative indices can also be used to specify axis. The ith axis of the returned array will correspond to the axis of the input, if not specified, which reverses the order of axis. Okay, so you just want to have a permutation of this so that it can convert it to that basically. So okay, so what we want is, it is very similar to our what was I just saying, torch.permute basically. It is exactly the same. So what you want is, you want to keep the first axis as the first axis, you want to keep your second axis as your new one, and not second, it is third, and 1 2. So this is your code. So now your image is BCHW, which your ONNX model is expecting. So if you print your image shape node now, you will see what you have. I want to print this right now, we'll print it later. So here we are just going to return the image, and we'll just say, let's call it not preprocessor, image loader for now. We'll have a preprocessor later. So our image will be image loader, and we'll give in our image path. So this will be our image, our preprocessed image, and now we can just directly pass it to this. Now it should work. Enough goofing around. Please, ONNX, stop torturing us. And still doesn't work. What happened now? We forgot to convert it to new data type. So as type np.float 32, and now it'll work, right? Still doesn't work. Why? And we forgot to resize as well. Are you kidding me? So we'll say image is equal to cv2 dot resize, and we'll say our path source is our image and our new dimensions are 640 640, and we'll also want to specify, just for the sake of it, I think by default it also uses this as well, but dot interlinear. Let's run this, boom. Finally, after so much effort, so much pre-processing, we are finally able to achieve an output from our ONNX-Runtime. But what is the shape of this output? What does this output actually look like? Let's analyze that for now. So we'll keep again plotting the images too far away. We are not even able to interpret what the results are right now. So we'll go to our outputs and we see what it looks like. So output 0. Okay, you have an array. So outputs 1. List index out of range. So okay, so you only have output 0, and that is a tensor, right? So let me just do type. But tensor I'm also mean numpy array. So yeah. And okay, so you see all of these things now, but what is this output? Like, it's where is my x y? Where are my 4 points? What is this? So here you have 1 comma 20 comma 8400 outputs. So basically, when we trained the model, we didn't look at Ultralytics enough, and the maximum number of bounding boxes that could be detected were 8400, 8400 for that matter. Now, how do you deal with this? Basically, if you are aware of YOLO and the pipeline, there is a technique which is used, which is non-maximum suppression. So you detect all of these boxes, which is a large chunk of boxes, and then you run non-maximum suppression on them to combine these boxes and finally get the perfect prediction that you are expecting. So what is non-maximum suppression? It is a technique where you calculate the IOU of two or more boxes, then you see. So okay, so how do you generally do that? You have a classification score for each of your labels, right? So you arrange your boxes in terms of your classification score, and the one with the max score gets to be the first. So you pick up that up, you see the next box, you calculate the IOU, you specify a IOU threshold. Now if the threshold matches, like if the threshold of IOU is greater than uh, like if the particular IOU is greater than the threshold is what I'm trying to say, but let me quickly show you what is intersection over union. So the higher the intersection over union, it means the images or the bounding boxes are very close to each other. So it is the area of intersection divided by area of union. Very simple, right? So what you are calculating in this is, so you get your maximum classification score prediction, you check the box after it, you see what is the IOU of that box with that particular box you have in right now. If the IOU is greater than the threshold, then you combine both of these boxes and you have your new box. Then you keep doing the same for all of the boxes, since until and unless you are left with only a few amount of boxes, and that's when you finally have your detection prediction. So this is what is non-maximum suppression, and this is how you use the IOU metric inside of it. Now, this is something that we'll have to do as a post-processing on these results if we actually want to get the results from the ONNX runtime in our clean XYXY, XYWHR, those kind of formats that were being used by Ultralytics when we just saw the inference there. Now, how can we do that? So, we don't want to write soft NMS or NMS from scratch on ourselves. Now, I just randomly saved soft NMS. What the fuck is that? Why am I adding soft beneath of it? So basically, NMS is a great technique. It was what originated all of this because initially you get all of these boxes, you don't know what to do with it, you don't have an NN that can accurately predict the boxes that you want, and it worked out amazingly. And then after that, as with anything else, there is always room for improvement, and adding the soft behind NMS was that room for improvement. So this paper was published, which in the same NMS technique that I just explained to you, where you have a box, you calculate the IOU with all the other boxes that you have predicted, you see if the IOU is greater than the threshold. If it is, you combine both of the boxes. You want to do the same thing, but instead of how we were performing it greedily in our normal non-maximum subtraction, that your box is merged now and this is your new box, instead of doing it like that, that you get the maximum classification score, you give scores based on IOUs and you are left with best boxes as such. So you can go through this paper for more detail. I don't want to go into much detail for now, but basically you stop assigning these weights, like combining these bounding boxes in a greedy fashion. Instead of doing that, you want to do that in a softer way by just giving them scores and finally picking up the top scores based on the confidence threshold that you have given. So when you're running the ONNX model, you have two more inputs that you can provide in here when you're loading the path, which is your confidence score, which is not visible here, but you can give that. And I'm not sure how I figured that out. But yeah, so you can just say your confidence threshold to be anything, and you can also set your IOU threshold. So this is what you have. So your IOU threshold is how much the boxes should overlap for them to be merged into a single box, and your confidence threshold is what what boxes do you actually want to consider. So any boxes that have a confidence in classification less than 0.45, I will directly discard them. But before doing that, I'll apply a soft NMS layer to them. In the hard NMS layer, what I've or the traditional NMS, what I would have done is I would have directly removed these boxes, but instead of doing that, I'm first assigning new scores based on the combination of different boxes, calculating their IOU, and there is a very simple formula to it. If you can quickly show you, you can go through the paper in detail, but just to quickly show you what we are trying to do, this is the formula in IOU. So if your IOU is less than the particular threshold, then you give it the score whatever it is. And if your IOU is greater than the threshold, then you give it a score of 0. That's what you were doing in your traditional NMS, that once it has reached that particular intersection over union threshold, you want to just discard the image, you give it a score of 0, it will never be picked. But instead of doing that, in your soft NMS, what you're doing is, if your IOU is less than your threshold, then again you give it the same score because there is no intersection between them. But if the intersection over union is greater than a particular score, then you want to reduce the score by this function, because your intersection over union will always be less than 1, so this will always reduce the score, and this will give you softer scores for boxes that have some intersection, but also at the same time allow you to at least have them, because sometimes it can be the case that those boxes are actually your true prediction. And that's why using soft NMS directly gave you performance boosts that they have showcased in this paper that you will have to read, because I'm not going to be reading this paper in this video. But yeah, these are the best kind of papers, because you just change one small thing in the formula and you get performance improvements everywhere. Now, to apply soft NMS, I'm not going to be applying soft NMS from scratch. Again, too much task for me. But there is a GitHub repository where they have applied soft NMS from scratch. So we will be using that. Let me just quickly see. Now, the one thing is that I want to use pure NumPy. I don't want to use anything else here. That's not what we play with. So I think rotate CPU, soft NMS rotate CPU was the library. CPU implementation of soft NMS for rotated rectangles. This is exactly what we want. So here, this guy has implemented the soft NMS rotate CPU, where you want to input in the format of XYWH theta, which is your R, which you are referring to in your YOLO predictions, and you give in your scores, which is your classification scores from your model, you give in your thresholds, and finally you give it your final threshold, They have named it final threshold and stuff, but this is your confidence score, and this is your intersection over union threshold, which will be like how much intersection should there be so that the boxes can be considered as one. Now, one more interesting thing that I want to tell you is that soft NMS, if you will go through the paper itself, you'll get to know this, but I just found it pretty cool, so I just want to let you know that soft NMS also has something amazing where, like, they observe that applying soft NMS reduces the dependence on hyperparameters like the confidence score and your IOU threshold. The dependence on these parameters are reduced when you're using soft NMS as compared to your traditional NMS. And that is amazing. Like, you see, your this is your I think these are your, no, the, what was it? I think the one with sigma are your soft NMS. Yeah, okay, here it is. The sigma ones are your soft NMS and your anti ones are hard NMS. Now, if you see this, look at the distribution. You'll see that when you have the one with the sigma, so the green and the red ones, doesn't their MAE, I think MAE, AP, yeah, average precision they have calculated here. So their average precision doesn't really plateau too much when you change the confidence thresholds, which makes it great for us because we don't want to deal with that and do too much experiments. We'll just keep it somewhere in the middle and we'll know that this we're applying soft NMS and it is going to be good for us. This is the plus point we are getting from Ultralytics because Ultralytics applies traditional NMS and we are here applying soft NMS. So cool. Now that we understand and we are on the same page on this, we just want to copy this code and apply this. So I'll just download this raw file into my YOLO and ONNX blah blah blah. What the hell am I even speaking? Am I having a stroke? No, hope not. I'll just save it here. Now you have your soft NMS.rotate function, which will require your scores and your prediction boxes. Now we'll have to figure out some way of giving them as well. We are not over yet. So now the question comes down to how do I want to process my output so that I can get the prediction scores from it and also get my prediction scores from it and also my predictions where my boxes are actually located. So when I face this problem, how did I fucking solve this? I don't think you have to do much. All you got to do is you get your row output. Okay, so let's see. So we'll still try to figure it right here. I wanna do this exercise with you. I have done it once. I didn't complete it completely. Yeah, complete it completely. Wow, it's the genius. But okay, so just wanna quickly do this. So your outputs have your predictions as well as your confidence scores. So to extract it from there, uh, your output size is this, and as I already told you, like, these are your actual classes. This is what you have. So for example, when you're training a OBB model, you're training your YOLO to output X, Y, WHR. So I'll just open some docs just to so that you can read properly. So when you're training a YOLO model, you give it X, Y, WHR, which is your so if this makes sense, so this is your X center, this is your Y center of the box, this is the width of the box, this is the height of the box, and this is the rotation of your box. These are the things you require to train a model on a oriented bounding box task. Other than these features, you will also require your classification features, and your classification would be uh, which class your model belongs to, and at the same time, what is the confidence probability on it. So to do this, what we generally do is that your class scores, correct? If I'm getting this correctly, your class scores is stored. Okay, 2, 3, 4. Okay. So now again, this took me a little bit of experimentation at the time being. It is not something that is clear, and you will have to read the GitHub implementation of Ultralytics to understand this. But what actually happens is, or I can just show it to you. Maybe I can just quickly find it. So, can I quickly find it? I hope I can. Models, YOLO, OBB, and you have your predict here. So when you're predicting your post-processing stuff, you're applying non-maximum compression, you're getting your confidence, your IOU, and you must be sending in where are you sending on your predictions. Yeah, there you are. So if I can show you this, that would be great. What the predictions look like. Yes, prediction is a torch.tensor, batch size, num classes for flows plus num masks, then your number of boxes. So correct, this is what exactly what I wanted to show you. So you have your number of classes plus 4 plus number of masks, and for rotation you also have an R component in there, which I think they have not mentioned, which made it pretty tricky. I think they are just doing that if R or something, they are changing their conditions a little bit. That's why I had to read this code multiple times to actually understand where we are getting the values from. But I have gone through the trouble and I finally have the results for you. So what you can do is to get your class scores, that is to get your class scores, you just have to uh, get your output. Let's call it row output just to remove any confusion, as we'll be processing it multiple times to actually get it in our desired format. Then you take your row output, you pick the 4 plus number of classes. So what did we do here? And you pick all of the rows. So what am I doing here is that I'm saying that the 0 1 through 3, so position 0 comma 1 comma 2 comma 3 are my x y w h, correct? And then after these positions I have my class scores. Class scores would be my number of classes. So if I quickly check my, okay, I didn't copy it, so where is my .yaml file? There you go. If you see here, I have 15 classes. So my number of classes is 15. I probably want to need this, so I'll just copy this and I'll make it more standardized because you want to run this every time. So I'll try YAML loader. Okay, let's say we get the number of classes for now. So it's 15. We'll fix it. We'll keep it more modular. In this video we are just trying to get some predictions. This preprocessor right now is also very tricky because YOLO, Ultralytics YOLO uses some interesting pre-processing techniques that we are not using right now, which means that our output will not be the same, but that is a bit of a spoiler right now. And I shouldn't have shared that, but okay. So you have your number of classes, you have everything. Let's clear everything and restart. This will also make sure that everything is working correctly. So I do this, I load my image, give in my number of classes, and I run my model, I get my row outputs, I print them, and I have my class course here. Now what do I do with my class course? And at the same time, I think I can quickly say the row output shape has this. I don't want that, so I can just say is row output dot squeeze, as I don't want my first dimension to be there. List object has no attribute squeeze. Oh, am I working on row output 0? So okay, I'll just say row output 0 and say row output is equal to row output dot squeeze. Cool. So now what I'm saying is we see the shape that is 1 comma 20 comma 8400. Now the 8400 are the maximum amount of boxes that will be detected by the YOLO model. 20 is my, so as I was explaining you in this 20, so I have 20 positions in total. My first 4 indexes are my x5wh, and after that I get, so the number of classes I have, which is 15 in our case, are my number of classification scores. So I'll get a classification score for each of them. So let's say we have something like whatever you can say from 4 to 18. This will make up 14 numbers, right? Yeah, both inclusive. So I think with Pythonistas are not exclusive, not habitual to it. So let me write it in this mathematical notation or whatever. Let's do this in this. These indices are my classification scores. And finally, I'm left with my last index, 19, which is my rotation, R. So it's kind of weird that they have arranged it in this way, that they have kept the rotation completely different to all the classification scores. I was gonna, like, it could have been XYWHR and then all the classification scores, but they have kept this way, and the model is trained like this, so we have to follow this structure now, and this is how you get all your outputs. So now I have my classification scores. I want my classes, I want my mask coefficients and my boxes with the rotation parameter in them. So let's get started with that. Okay, so just to summarize what we have done till now, we have loaded up our model, we have created our image preprocessors that can at least run on our ONNX-Runtime session. We are getting our raw output. The raw output seems weird. We were not getting this kind of a shape when we were running this in Ultralytics, and now we are trying to post process this so that we can finally achieve our XY boxes or some kind of a beautiful format that we can post process into whatever we want. So how do we do that? Now, in the same time, we also discussed about soft NMS, and we said that to get our final boxes, which are our final predictions, we'll need to run them through soft NMS. Now, we're not using NMS, which is used by Ultralytics, and this is our plus point from Ultralytics because NMS has shown better results overall in our research papers. So ONNX-Runtime should give you better accuracy, like the ONNX-Runtime pipeline that we are making to run your Ultralytics trained models. So cool. Now to run and soft NMS rotate, we want our boxes which are in our XYWHR format and R should be in degrees. Then you want your scores, which is your classification scores for each boxes, and that's it. These are the two things you want from your model. Now, one more trick that you commonly use when you are doing this is that, okay, when you are computing the our overlap, our IOU, you sometimes don't want to compute overlap between different classes, as it might be possible that one class rotated box is here and another class rotated box is slightly overlapping the image. That's why they are overlapping. So you don't want to do that IOU thing you're doing on different classes. To avoid that, you basically offset the images with their classification scores, offset the detections basically, so that their IOU is detected differently. Now to do that, let me quickly write the code for you, that how we can get this row output from this shape to our final boxes. So you get your classification scores, we finally have them. Now these are of the shape that you have your 4 classes and your number of boxes, 4 comma num boxes. I think we can just transpose this for better, but okay. Now you have this. Again, you will need your confidence scores. Confidence scores will be your class scores. So you just want to calculate the maximum out of them. Comma dim is equal to 1. So from num boxes, okay, no. Dim you want to keep 0, right? Yes. I think dim, fuck this confusion. In torch you use dim, in numpy you use this thing. Right, okay. And your classes would again, so you have your confidence score. This is your confidence score. And then you have your class score, which will be your, not even class score, your classes directly. So classes would be np.argmax. So you do the pretty much the same thing, and you do class course comma axis is equal to 0 again. Or maybe we can just transpose this, because I think being a Pytorch user, I've been constantly been habitual of having my batches first and my classes later. I think that's why in the code I'm using, in the previous code that I wrote on my own, I also did the transpose there. And there's no good reason for it other than just a force of habit. So there you go. You have your classes, you have your confidence scores. Now what you want to do is you want to sort your indexes based on your confidence scores. So sorted would look like, now why do we want to do this? Okay, let's try to understand it problem by problem. Otherwise I'll just be showing you my code directly. There's no point in solving this together. So you have your class scores, you have your confidence scores, and you have finally achieved your classes. Now what is happening is, you want, so your boxes you have, right? So you will get your boxes from the first four, and let's quickly get our boxes as well. So how will you get your boxes? So for boxes you need your x5wh component, which is directly which is pretty easy, right? You go to your row output, you select the first four rows, and you have it. This is pretty much it. You get your boxes. Now you also want your rotation element. So rotation is equal to, so let's call it xy_wh, and your r is equal to row output, and your final, like the last index you have there, and this is your row output, and you want to say boxes is equal to, do you want to do something on the r? So we'll have to check. Okay, so let's check this out. What is the format of our r for now? So we know the rotation is not varying too much, right? So we know for sure that at least, like it shouldn't be too high. Like if it is, we should be able to sense if it is in degrees or it is in theta. So let's see what our r is in. So let's just print r for now. Yeah, there you go. So it is minus 0.14, so minus 0.2. So I think this is not, this is radians, right? This looks like radians. um yeah, I think these are radians. uh did I make sure of this previously? I thought they were radians. um Whatever. Rotation, where is it? Row output dot squeeze. Okay, I'm not seeing anything right now. Yes, I'm sending these boxes np dot zeros boxes dot shape. Dude, what the fuck have I even done? Yeah, that's why I have to work on this problem again. I'm completely out of it. But yeah, so this must be your, so x5wh and then your r. So your last index must be a rotation index. For some reason I'm not seeing it in the previous implementation. I don't know how I achieved it then. I'm doing something wrong. 0, 1, 2, 3. Okay. Just give me a second, guys. Boxes of 0.1 plus offset class. Where the hell am I giving rotation then? I'm not, man. For IUU calculation, I'm not giving rotation. That's not cool. Maybe I have missed somehow. Okay. Maybe we have missed it somehow. That's interesting. So we have an upgrade. So if I multiply it by what? So to get it into degrees, I just want to do 180 by pi, right? 180 divided by np dot pi. I don't think it will be this. So let's run this again. minus 11 degrees, like let's just print out the maximum of this just to see like is our interpretation correct or not. 100 degrees. 100 degrees is too much. You can't get 100 degrees in this, right? Oh, 90 is the maximum you can go to. What the fuck fits with 100? You have it like this. Okay, it makes sense in a way. But can it be 100? We can look at our image. This is the image we are using, and we have seen the detection boxes formed on this image. I don't think none of them are 100. Well, it depends on like what you're doing, like anti-clockwise or clockwise. But I think generally you do anti-clockwise only, so none of them seems to be 100. Okay, and if I do it without this, without my theta conversion, maximum is 1.72. So does that make more sense? Like NMS is to be computed on them, so you can't be certain. But okay, skip. So this we can see more in the final result. So let's keep it like this for now. And you have your XYWHR, uh, which is finally your boxes in a sense. I don't need to write them separately. And which is your np dot concatenate your XYWH comma R. You want to give them as a list. XYWH comma R, and you want to specify your x's. X's is going to be 1 for us. Or no, we have not transposed them yet. Have we? No, we have not. So maybe we can just transpose our row output. That would be the cleanest way of doing this. Why to suffer? When you're squeezed it, you just finally transpose it, and there you go. So now what you have to do is you don't need to transpose this again and again. You don't pick from here, you pick from there, and also same way here, you don't pick this from here, you rather pick this from there, again the same way around, and there you go. So now you want to do it against xs1, and classes and stuff, when you're calculating, you want to do it against xs0, or no, okay, no, that is correct. Cool. So now everything is correct. Now we are getting our boxes. Let's just print our boxes shape just to be sure. All the input arrays must have the same number of dimensions, but the array at index 0 and 2 has dimension. Okay, so we'll just have to unsqueeze this on dimension 1. Or you just add a new axis. That also works. And this is super clean. I love this. So you have your or no, not like this. You want this before, and then you want your np.new axis, because you know these are your number of samples, and that. So let's see now. All input arrays must have same dimensions. The array at index 0 has 2 dimensions, and the array at index 1 has 1 dimension. Why is that happening? Print r.shape. Oh, that's why it's happening. Why is it like this? Oh, okay, I'm running a max on it, that's why. Oh, I forgot I was running a max on it. Now it's working. Now it's working, and we're getting our final shape, which is 8400 by 5, where we are XYWHR. This is the output we want to run our soft NMX. And we also have our confidence scores, so we can quickly run our soft NMX compute on this now. Amazing. Now this will return us indices, I think. Let's remove this. Okay, we can look at the tests they are doing. So you have your boxes, which are XYWHR, and this is in degrees. Then you given your scores, which should match your 1 2 3 4 1 2 3 4, so it should match the number of rows, makes sense. And then you given your confidence threshold and stuff, and it gives you a result, which is your list as much as I remember. So we'll just go into our terminal and ls python soft nms rotate.py 012. So yeah, it gives you a list of indices. Now, one thing you have to make sure when you're giving an indices like this is that you don't wanna. Okay, and one more thing I observe is that it has given the scores in sorted order. So I think as I told you in the soft NMS implementation that you want to sort your scores before giving them in. So I think we need to do that here as well. So what I'm gonna do is class scores I have. So I'll say sorted indices is equal to np.arg sort. So it will give me the indices of what the correct sorting looks like, and then I'll just have these sorted indices which I'm going to be applying everywhere basically. And yeah, dim is gonna access is gonna be 0 by default. And so yeah, this is gonna sort the indices based on our confidence score. You do this, you get your confidence scores from here. um, so class scores I have, no, you will have to do it on confidence scores, that will be stupid. So let's move this. um, so your confidence scores, let's print the shape of confidence scores just to make sure. That shape is such a great helper when you're working with matrices. Shape can allow you to work with everything. So yeah, access is going to be 0. You have your sorted indices, and you just do is that sorted confidence scores is equal to confidence scores sorted indices, and you do the same for your classes. Is equal to, first you form your classes. So there you go, and finally you sort your classes based on your sorted indices. Do you do the same with your boxes? So boxes is gonna be if I can just type, and your all the columns, we'll just print the boxes shape for now just to make sure, and you should have your, okay, what the fuck is this 15? Where the fuck did this 15 come from? Excuse me, we didn't have a 15 just a second ago. What the fuck did I fuck up this time? So you get your class scores, you get your sorted classes, and you have your row output. You do this with your row output, you create your boxes. Before doing this, is the shape correct? No, it's not. What am I printing them? No, the box, no, the shape is correct before it. Okay, so what am I messing up here? This am I messing up? Dude, what the hell is happening to my boxes? Adding the sorted indices fucked it up. Oh, how can you do that? Oh, guys, come on. What dumbness are we doing here? Boxes, we want to sort on the first index, and we want everything from the second index. This should help it sort. So let's just print sorted indices again. Sorted indices dot shape. Oh, sorted indices dot shape is fucked in itself. Sorted indices shouldn't be this. What happened to it? Okay, let's quickly review our code, whatever we have done till now. I don't think we'll need the documentation anymore. We are done with that. Thank you. Cool, the screen is finally bigger now. I can finally see, for God's sake. Let's restart for now, and let's just look at whatever the fuck we have done to this. So we have your class scores. You calculate your confidence scores. Your confidence score should be, yeah, np.max at access1. Then you calculate your, oh, and someone messed this up. Confidence scores on access you don't even need to specify. So you get your confidence scores, and yeah, everything should be working hunky dory from here on after. 8400,5. Now that you have all of these things with you, now we can finally run our soft NMS. So let's import this. So import soft NMS rotate from soft NMS rotate. Import soft NMS rotate CPU. No. Run this row output, and you have your boxes. And what you can do with your boxes, something really cool. You can just say that your keep, which is the indexes you finally want to keep, is equal to soft NMS rotate. You give in your boxes, you give in your confidence scores, and that is all that you need. IU threshold, if you want to give, you can give 0.45, 0.1, whatever, it will not matter. And that's all. Now let me just print to keep, and let's see what we get. So NMS is running on it. NMS is taking a bit of a while. NMS is comparatively slow because it has to go through all of these 8400 boxes and calculate that IOU and stuff. Let's see what we get from here. Okay, it shouldn't be this slow. This is super slow. And did we fuck it up? It's stuck somewhere else, is it? I'll just restart this. Sometimes Jupyter just acts up, or maybe my PC is just getting old. Well, only if you were subscribing, I would have enough money to buy a better PC and a better graphic card to teach you more amazing things. That's the only intention. But okay, let's see. Okay, it is running. It is taking a while. Okay, let's wait for it. Damn, man, it's already been 2 hours. So I think we have managed to achieve enough in this video. Like, we are able to set up our NMS, we are able to get our boxes. I hope this access made sense to you the way they are in your Ultralytics YOLO. I'm still not sure why it's taking this while. And there you finally go. You have your access returned to you. Now these are a lot of access. Like, let's just print the, I want to run this again, but print length of to keep 3896. That's crazy. That shouldn't be there. Nah, I don't trust this. This is wrong. Now why can it be wrong? Have I mixed up the IOU threshold and stuff like that? Soft NMS rotate. And how do you do this? You're doing final threshold and IOU threshold. So yeah, I have messed up the thresholds. So let's pause this for now. You generally have a lower IOU threshold and a higher final threshold. Restart, clear all easy stuff now, and we run this. It should happen faster now because we have a lower final threshold, and the length should also satisfy our logic. There is one more thing that we are missing right now, and that will be our last step for this video, where we want to offset our images based on their particular classes. Now you ask, why do we want to do this? Because as I just told you, that if you have multiple classes, there can be some overlap in the image itself on those classes. So you don't necessarily want to calculate the IO threshold on overlapping classes and say that the superior one won. Instead of doing that, one better thing you can do is just directly use your different classes. So you offset those classes, you offset the boxes by those classes, and you're pretty sure that they will never overlap now because you offset them by the size of the image itself. And then using those offsetted classes, you are able to compute the overlays or the that IOU that you are detecting. You will only be detecting it for your particular classes per class. So that should help you a lot. Now we're getting a lot of predictions. This makes no sense. We shouldn't get these many. What are we doing wrong? We're doing something wrong. Is it the rotation part? It can be. Or is it something else? We want to calculate the rotated bounding boxes. What are we doing wrong? Yeah, you get that. Yeah, that everything is correct. You get your boxes like this. And we have not offset them for now, but offsetting them is really easy. What you want to do is, so okay, let's create the offset also, just to make sure we haven't left anything unturned. So offset classes is equal to so whatever are your classes that you calculated right now, you do that, you take that and you take all the rows, you create a new axis. And what you want to do with this is that you just want to add everything to a, like you want to add x, y, w, h with these particular values, right? So to achieve that, you just say that, okay, so you do np.concatenate offset class, comma, your np.zeros. Yeah, I need to find a better way for this. I've kept it for like this for now. Okay. And finally, you given your axis, which is 1. And you give your image size, which is 640 for now. So what we are doing here is, if you can see that you have your offset classes, and whatever that they might be, you are offsetting your x with them. So your x is filled up with your classes, so your classes can be 0, 1, 2, 3, 4 till 15. Now we are getting all of these classes in this first axis, and we are adding the other 4 x's, we are adding zeros, and we are multiplying it with the image size. So finally, what you are getting is a matrix where the first row will be multiplied with your image size and the class you are at. So every image will be offsetted in x with that particular offset, which is your image size. So you will be only doing in class comparisons when you are calculating your NMS and doing your IOU. So yeah, that makes sense. So I'll just create the final result, which would be boxes. No, we're not on the final result yet. Sorry. Oh God, what the hell? You don't do that. So you have your offset classes. Yeah, so create your classes. You do your offset class. You offset your classes. So in the boxes, you just want to add them. So this is pretty straightforward, because they are of the same size now. So you just go on and boxes plus offset class. So this should allow you to offset your boxes. And yeah, everything in the boxes part is same. I don't think I've done any mistake there. And you just want to calculate your, okay, so why are we not getting the results? Hmm. You have transposed this. Why have I transposed this? Because okay, my boxes are in correct shape, right? because yeah, okay. Sorted indexes come up on plus offset. Okay, yeah, that is correct. Everything is correct now. But I'm still getting a lot of boxes that I shouldn't be getting. Now, it can be the model is shitty right now, or it can be that the preprocessor that I'm working with is not good enough. So, we are offsetting the classes, we are doing everything correct, but you are still not getting good enough data. Now, what is this? np.code concatenate np.zeros. I think this thing is, you just want a tuple. Yeah, that's the issue. Okay, so I think the issue, there can be two possible issues. So we didn't take a very well-trained model. So it can be that the confidence is very high in most of the cases or something like that. That's why we are picking up so many images. Or it can be that our preprocessor is fucked. So as I told you that YOLO uses some specific preprocessing steps when training the model. And here the preprocessor that we have written doesn't really qualify as the correct preprocessing that the YOLO model requires. So what to do with the YOLO model preprocessing? So to understand that or to discover that, you will have to go through the Ultralytics GitHub page where they have best precaution. I have to do DSA. Every turning stone reminds me that I have to get back to DSA and improve there. Yeah, I'll do that. Trust me, guys. Trust me. We can do it on channel as well. We can make some videos. Yeah, that will be easier for me and for you because you will be keeping me accountable. That's for me. But okay, so if you go here and you go in the models, you go in your YOLO models and OBB, and then you're predicting. And when you're predicting, you go ahead and see, oh, where am I pre-processing the images? And you, if I can just find them. Okay, this is just post processor. So I think maybe somewhere in the detection predictor. Oh, they have the same, I guess. So here did I have the preprocessor written? No. Then the base predictor, this base predictor has the preprocessing steps. So there you go. So this is the preprocessing they are doing right now. We'll just copy this for now and see what all do we need to do from this. So let's copy it up and see. So not tensor, we are not using tensor, so doesn't matter to us. So image is equal to np stack dot pre-transform self dot pre-transform bgr to rgb and bhwc to, so this all we have already done, so we don't need to worry about this. As contiguous array, I don't think we also need to do this. Image stores dot from numpy, again we don't need to do this. Image is equal to np.set. Okay, so now I finally see the issue. They are dividing the image by 255. We are not doing this. So what's happening is, well, we are detecting a lot of boxes because all the pixel values are like exaggerated by 255. So let's return image divided by 255.0 and let's restart this, clear all, and let's see if we are finally able to achieve the outputs of our dreams from this. And there you see you get 12 boxes now, which is good. You get your final result as 12 boxes, so final result is gonna be boxes and to keep. So you get your two boxes. These are your all of your boxes with XYWHR. And in this, what you want to do is, but okay, there is some, we didn't still look at the pre-transform thing. So I want to keep the post-processing thing for the next video because I think this video is already preceding the time limit that I thought I'll be requiring for this. So let me just quickly finish with the pre-processor and then we can go ahead with the post-processor in the next video. So in the pre-transform things, okay, what the hell are they doing here? So you send in your image size, use model strides or whatever, and auto same shape and something like that. So let's go and see what's this letterbox all about. Where the hell is it? Pre-transform, new shape, auto fold, new shape, auto scale up fold, blah blah blah. When you call it, if labels is done, label dot get image, doesn't matter. what is all of this? Okay, so they are, yeah, as I told you, they do some weird pre-processing on their images. I don't know why, but I guess I mean I understand why. Maybe they just show the best results like this, and that's why they want to do it like this. But yeah, we don't want to suffer too much. I have suffered once. So what you do is you give in your image path, and now we also give it the image size which the model is expecting. So let's keep it as 640, and what you want to do is you say your current image shape. So shape, so you load your image, you say your shape is equal to image dot shape to, not this, this, and so you get your shape, new shape is equal to size, image size, I guess. You get these, and then with these two images, uh, okay, this is a cool thing I've done. So if new image is not is instance int, class or tuple, yes. So if is instance new shape, image size of int, then image size is equal to 640 comma 640, or why am I being an idiot, image size comma image size. So this is what I want to do, and then here I'll say scale ratio new to old. So r, this is my ratio, is equal to min image size 0 comma shape 0. So I'm just trying to calculate my ratios, and this code is like directly taken up from uh, the Ultralytics code that I just show you. So there is not much to discuss here. Ratio is equal to r comma r, width height ratios, and then you create new unpad, and you say int round. There's a lot of things going on in this, but yeah, basically you want to do this, and you want to do the same thing for your y-axis into r, and then you're doing this in the currently you're doing this in your HWC only. You have not converted the image. So yeah, I mentioned all of these things. So that's why we are taking up our y, like our second axis first, which is actually our x here, and this is our y. So yeah, so the new unpad is this. Then we say dw comma dh is equal to new shape, which is our image size 1 minus new unpad 0. New image size 0 minus new unpad 1. Now again, don't try to understand this all too much. If you want to though, I'm not discouraging you. You can go ahead and read the this class basically, which they are using as a pre-transformer. I have gone through this once, so I know all kind of pre-processing they are doing for their OBB models, which is basically same for all of their models. So this part we will only have to do once, whether we are creating our detection model, our segmentation model, or our classifier, or whatever. So I hope this will remain the same, such that, and then you just finally do dw divide equal to dh divide equal to, and if shape I guess we can just use this one. So yeah, okay, that's why I mentioned interlinear in it, because I guess I must have read it there that they are using interlinear, and that's why I used their code directly. Cool. So this is it, right? And we don't want to mention it like this because we have already converted it into a tuple in any case. So this is it, right? You convert your image into this. And once you have done that, you have to still do some things. Top comma bottom is equal to int round dh. I suffered. I remember everything now. How much I had to go through this code to understand it, and I finally decided that maybe it is a good time for another day. I just want things to work exactly. And int round dw minus 0.1, or I'm wrong again, dh plus 0.1, correct. And you do the same for left comma right, which is your int round dw minus 0.1 and your int round dw plus 0.1, and you just say image is equal to cv2 dot copy make border image comma top comma bottom comma left comma right comma cv2 dot border constant, and your value is gonna be 114 114 114. So for some reason we are adding border in our images, and you finally say image is equal to, where did this image came from? This is nothing, right? What is this image? Is there something? Am I missing something? Why I haven't done this ratio thing? You don't need this. I don't know why I did that. Now, yeah, and also, so this all is working now, and finally, when you have image np.stack image, and finally you can say image is equal to image. Now you are doing the standard things that we did, that you add a new axis for your batch, and then you converted this into your bgr image. From bgr you converted it to rpg. So for that you just did, you have all of your dimensions, and finally -1. Yep, makes sense. And transpose, as we did earlier, we'll just do 0 3 1 2, and finally you should be able to get, okay, and you do image. Okay, so you have to do that image dot np dot as contiguous array image comma d type is equal to np dot 432. So that should be all. Image is equal, divide by equal to 255, and you return your image. So this should finally get you what you want. All of the pre-processing are done, and then let's see if we are getting the correct output. We're still getting 15.1, but okay, I think we'll fix the preprocessor later, and we also have to add the post-processor, so stay tuned. For now, we have most of the things running. I hope you understand how YOLO finally gives you the output, and also what all goes into the pre-processing and post-processing when, and whatever goes under the hood of YOLO itself. Now in the next video, we'll fix the preprocessor. We'll see how we can get the exact output as we get from the Ultralytics model. And yeah, this is the exercise we have to do for all three models. So yeah, cool. See you in the next live stream. Bye bye.